Okay, good morning. So let us start off. The other time we were to start with what we have statics. This is we're going to look at moments and couples. So we are going to look at statics, and statics we are going to look at mainly moments and couples. Moments is not something very new to you. A couple is not something very new to you, okay? And when we are talking about statics, it is just a branch of mechanics. And this branch of mechanics mainly looks at the rigid bodies and when or the conditions under which these rigid bodies can be in equilibrium, okay? Do we know the conditions for any rigid body to be in equilibrium? There are mainly two conditions for a given body to be in equilibrium. What are those conditions? One, we know them, we studied them in O level. What are the two conditions for a rigid body or for a body to be in equilibrium? Or when do we say the body is in equilibrium? Do we still remember them? When do we say the body is in equilibrium? Quiet class? Do we still know? Yes. Very good. When the sum of anti-clockwise moments about a given point is equal to the sum of anti-clockwise moments about the same what? The same point. And that same point we are talking about is what we call the turning point, or the pivot, or the fulcrum. Okay? That is the turning point. Or we can say the sum of moments about a given point. And the sum of moments about a given point is what we call a torque. Sum of moments or a torque about a given point is actually equal to the sum of other moments, again acting in the opposite direction about the same what? About the same point. Okay? That's number one. Okay? Number two, which other condition? One, we are saying the sum of clockwise moments should be equal to the sum of anti-clockwise moments about the same what? About the same point. Or we can say the algebraic sum of clockwise moments and anti-clockwise moments about the same point is numerically what? 0. Okay? When you add the sum of anti-clockwise moments, you add on to the sum of clockwise moments about the given point, the sum should be giving you what? 0. That is why we say the sum of anti-clockwise moments is equal to the sum of clockwise what? Moments. Is that okay? Very good. Now, what's the second condition for a body to be in equilibrium? The body to be in equilibrium, what's the second? That is one. But there are two conditions. We have already talked about one. Secondly, the resultant force that is acting on the body must be equal to what? 0. When we say the resultant force, then we are talking about the total upward forces. The sum of the upward forces acting on a given body should be equal to the sum of the downward forces acting on a given body. Okay? So, those are the two conditions. Let us write and say, this is the branch of mechanics. This is the branch of mechanics. This is the branch of mechanics that deals with the study of rigid bodies. That deals with the study of rigid. That deals with the study of rigid bodies. This is the branch of mechanics that deals with the study of rigid bodies, which are in equilibrium. Which are in equilibrium. Full stop. Which are in equilibrium. Full stop. Which are in equilibrium. Continue and say, a rigid body is said to be in equilibrium. A rigid body is said to be in equilibrium. A rigid body is said to be in equilibrium if it satisfies two conditions. A rigid body is said to be in equilibrium if it satisfies two conditions. A rigid body is said to be in equilibrium if it satisfies two conditions. Two conditions, if it satisfies two conditions, namely, if it satisfies two conditions, namely, the first condition, the writer say, the resultant force acting on it must be 0. That's the first condition. The resultant force acting on it must be 0. The resultant force acting on it must be 0. The resultant force acting on it must be 0. i.e., the resultant force acting on it must be 0. i.e., if F, like that, if F is the resultant force with two perpendicular components, if F is the resultant force with two perpendicular components, Fx and Fy, Fx and Fy, Fx and Fy, then for the body to be in equilibrium, for the body to be in equilibrium, F must be equal to what? F equal to 0. That force must be equal to 0. Implying that if this is equal to 0, then Fx should be equal to 0 and Fy must also be equal to what? 0. Implying that Fx equal to 0 and Fy equal to what? 0. That is that. Okay? That is when we say the sum of anti-clockwise moments, the sum of downward forces must be equal to the sum of the upward what? Forces. The resultant force acting on the body must be 0. Secondly, number two, we say the resultant moment or torque. That's the second condition. The resultant moment or torque. Another word or a single word to mean the resultant moment is torque. The resultant moment or torque. Okay? The resultant moment or torque of all the forces acting about a given axis. Of all the forces acting on a given axis, the resultant moment or torque of all the moments acting about a given axis must be zero. Must be zero. The resultant moment or torque of all the forces acting about a given axis must be zero. Full stop. Continue and say, this condition is sometimes expressed as a principle of moments. This condition is sometimes expressed as a principle of what? Of moments. This condition is sometimes expressed as a principle of moments. This condition is sometimes expressed as a principle of moments. Okay? i.e., sum of clockwise moments is equal to the sum of anti-clockwise moments. i.e., sum of clockwise moments, sum of clockwise moments is equal to the sum of anti-clockwise moments. Is equal to the sum of anti-clockwise moments about a given point. Is equal to the sum of anti-clockwise moments about a given point. Full stop. So I don't want you to stress yourselves when you are being asked to state conditions for a body to be in equilibrium. Then you'll be thinking, you'll be just there thinking, you want to write exactly what I've given you. Physics is physics and science is science. So what you know is what you write. The conditions are simply, if you cannot master whatever we have put here, it is the same expression, just a difference in words, but it is telling us the same thing. We have just two conditions for a given body to be in equilibrium. The sum of anticlockwise moments must be equal to the sum of anticlockwise moments about a given or the same point. Okay? Secondly, the sum of the upward forces must be equal to the sum of the downward what? Forces. As simple as that. Okay? You don't need to cram this and no, this is the same expression. It is the same thing that we are talking about. Okay? So let us, before we can look at something else, I need us to look at the types of equilibrium. We learned this in O level. Okay? Types of equilibrium. That's by the way, how many types of equilibrium do we have? How many types of equilibrium do we have? Do you remember? Do we know how many types of equilibrium do we have? Do we have only one? We have two, we have three, four, five. How many are there? There are how many? There are three types of equilibrium. Namely, one. I'm writing them. One. What's the first one? We are saying we have three types of equilibrium. What are they? One. We have stable equilibrium. That is right. That's correct. Secondly, we have stable equilibrium. That is right. Number two, we have what? Unstable. We have unstable equilibrium. Number three, we have stable, we have unstable. Then lastly, we have neutral. Yes, those are the three types of equilibrium that we have. But when we say the body is in a stable equilibrium, what does it mean? When do we say the body is having a stable equilibrium? Who can explain to us when we say the body is having stable, it is actually under stable equilibrium? What are we talking about? When is a body said to be in stable equilibrium? When do we say a body is in stable equilibrium? Do we know it? We don't know. Oh, okay. Can someone explain to us what stable equilibrium is about? Okay. When we are talking about stable equilibrium, it means when you displace a body, like when I place this duster like this, it is actually on a stable state of equilibrium. Reason being, if I am to displace this slightly, give it a slight displacement, let me move it like this, and then I release it, you'll see that this duster will go back to its original position of rest, okay, to its initial state of rest, even when I remove the what? The applied force. Check. It goes back. That is what we call stable equilibrium. In stable equilibrium, when you move the body, what you do, you will lower actually its center of what? Of gravity. And when you release, it goes back to the same state. It doesn't fall off. But when we talk of unstable equilibrium, I have a duster. Maybe if this duster stands like this, right? Okay? In this state, it is not in a stable what? Equilibrium. I say that. So when I put it like that, if I put it and then I remove the force, you see it falls off, okay? It falls off. So it does not go back to its original or initial position. It doesn't. It falls off, okay? That is the unstable state of equilibrium. But when we say it is on a neutral equilibrium, then it means when you actually move that body, you don't even change its center of gravity, okay? It's like you're moving this around this. We take a case of a cone. If you have a cone like this is a surface, and then like that, that's a cone. When you roll a cone on this desk, you find that you will not change its center of gravity. You don't raise it, you don't lower it. It remains the same. Okay? And the body does not fall off, but it can move from one point to another. Okay? That's a neutral equilibrium. It is not stable. It is not also unstable. Okay? It is just neutral. Okay? So we can take a case of a cone. If you have a cone with its base like this, which type of equilibrium will it possess? If you place a cone like that, what type of equilibrium is it going to possess? Stable or unstable? It is going to be stable. But if we happen to have this cone, what happens? Which one? This is unstable, stable, this is neutral. Okay? Let's write and say 1. Okay, before I say there are 3 types of equilibrium. There are 3 types of equilibrium, and this can be illustrated using a cone. There are 3 types of equilibrium, and this can be illustrated using a cone. Using a cone. This can be illustrated using a cone. One, say stable equilibrium. 1, stable equilibrium. 1. Stable equilibrium. And then we shall talk about stable equilibrium. Right hand side, a body is said to be in stable equilibrium if it returns to its equilibrium position. The body is said to be in stable equilibrium if it returns. A body is said to be in stable equilibrium if it returns to its equilibrium position. If it returns to its equilibrium position after it has been displaced slightly. If it returns to its equilibrium position after it has been displaced slightly. 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 Full stop. Draw this. Draw this one. Say this cone in this state is actually stable. Let's do it very fast. Must have this. This is the ground, Number 2, we are going to talk about unstable equilibrium. Secondly, unstable equilibrium. Unstable equilibrium. That is secondly, unstable equilibrium. We're going to talk about unstable equilibrium. Say, a body is said to be in unstable equilibrium. A body is said to be in unstable equilibrium if it doesn't return. The body is said to be in unstable equilibrium if it doesn't return. The body is said to be in unstable equilibrium if it doesn't return. If it doesn't return, if it doesn't return to its equilibrium position. If it doesn't return to its equilibrium position. If it doesn't return to its equilibrium position and it doesn't remain in the displaced position, and it doesn't remain, and it doesn't remain, and it doesn't remain in the displaced position, and it doesn't remain in the displaced position, and it doesn't remain in the displaced position after it has been displaced slightly. After it has been displaced slightly. After it has been displaced slightly. Very good. Draw the diagram. After it has been displaced slightly. The diagram is this. This is unstable. That is unstable. Good. Number 3, lastly, neutral equilibrium. Neutral equilibrium. Write and say, the body is said to be in neutral equilibrium. The body is said to be in neutral equilibrium. The body is said to be in neutral equilibrium if it stays in a displaced position. The body is said to be in neutral equilibrium if it stays in a displaced position. If it stays in a displaced position after it has been displaced slightly. The body is said to be in neutral equilibrium if it stays in a displaced position after it has been displaced slightly. After it has been displaced slightly. Full stop. If it stays in a displaced position after it has been displaced slightly. Draw this. It's neutral. Very good. Let us look at moments of a force. Moment, okay, we can call it a moment. Moment of a force. Moment of a force. Moment of a force. What is moment of a force? Okay, who can tell us what is really this moment we are talking about? Moment of a force. What's moment of a force? Yes. Your Maxwell. Yes, tell us. Can you say something about it? No. Yes, Leon. Moment of a force is actually the product of a force and its perpendicular distance from a turning what? From a turning point or from a given point. Okay? So when you multiply force and the distance from the turning point, you get what we call moment. Okay? So moment of a force of a given force produces what we call a turning effect. Okay? If I have this, okay, this one from here half to here, maybe this is my turning point. Okay, let me say this is a door and it's being inked at this point. For me to open it, I have to handle the door and then I pull it, or I open like that, or I pull it this side. Okay, so what I'm doing is I am producing a turning effect on this what? On the door. Okay, yes. And what I am, this is now moment of a force. What I'm applying, all of this becomes the moment of what? Of this force that I'm, okay? It is producing a turning effect, okay? So when I get the product of the force that my hand is applying on the ruler and the distance of this ruler from the turning point, it will give me what we call a moment of a force, okay? So it's just a turning effect. And the moment of a force is also called a torque. T-O-R-Q-U-E. Torque. So moment of a force is actually what we call a torque, a turning effect, the product of a force and its perpendicular distance from the turning what? From the turning point. So next time you find, instead of asking you to define moment of a force, someone is asking you to define a torque. Then you say, no, what is this one about? We are still asking you to define moment of force, product of the force, and its perpendicular distance from the turning what? Turning point. Right, I'll say, moment of a force, in bracket torque, is defined as, can just put here, in bracket torque. The way you have written it, it is fine. It is defined as a product of a force and its perpendicular distance. The product of a force and its perpendicular distance, and its perpendicular distance, and its perpendicular distance from the turning point. From the turning point. Okay? Or say is the product of a force and the perpendicular distance. It's the product of the force and the perpendicular distance is the product of the force and the perpendicular distance between the line of action of a force, between the line of action, between the line of action of the force and a given axis, and a given axis, and a given axis. So we have to take note of this. We are not saying moment of a force is the product of the force and its distance from the turning point. Are you getting the point? It is not just its distance from a given what? Not just any distance, but we are talking about the perpendicular what? Distance. Are you getting that? So we have to take note of that. We are going to look at cases where you find a force is at an angle. It is not perpendicular. Maybe it is inclined at an angle of 30 degrees or 60. And then for you, you just from nowhere, you want to take any distance. That will not be correct. Okay? So you must actually look at the force critically and then identify the force, its line of action, and its distance from a given axis. Especially where we are going to take moment about a given what? A given point, or what we are going to refer as our turning point. Okay? So you must know that it is a perpendicular distance, not any what? Any distance. The new narrator say, moment of a force is a measure of a turning effect. Moment of a force is a measure of the turning effect. Moment of a force is a measure of a turning effect. Moment of a force is a measure of a turning effect. Moment of a force is a measure of a turning effect. In bracket, rotational effect. In bracket, rotational what? Rotational effect. In bracket, rotational effect. Close the bracket. In bracket, rotational effect of a given force on a body about an axis. It's a measure of a turning effect, in bracket rotational effect of a given force on a body about an what? About an axis. Okay? Very good. In the new line that I say, the SI unit of moment of force is, the SI unit of moment of force is, what is it? What is its SI unit? It is Newton what? Newton meter. Capital N, small m. Newton meter. The SI unit of moment of a force is Newton meter, Nm. Because we are multiplying force, you know that moment is got by saying force times what? Distance. And force is in newtons, and distance is measured in what? Meters. So it is Newton what? Newton meter. In the new line, I can say, if force F acts on a body, 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 as shown in the diagram, 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 let us draw the diagram. Like that. Very good. Write and say after the diagram, the moment of a force F, the moment of a force F about O, the moment of 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 force F about O is given as FH. Is given as F what? Is given as FH. The moment of force F about O is given as F what? FH. Where H is what? Is the perpendicular distance. Where H is the perpendicular distance. Have we done that? Say again, in a new line, write and say, consider a uniform beam. Consider a uniform beam. Consider a uniform beam. Pivoted at its midpoint M. Consider a uniform beam pivoted at its midpoint M. Pivoted at its midpoint M. Pivoted at its point M. When we say a uniform beam, then it means if this is a uniform beam and it is 100 centimeters long, like a meter rule, say uniform meter rule, that means its weight will act at what? At the center, okay? At the center of this, which means it will be where the weight will act or where the center of gravity will be 50 centimeters from here to be 50 centimeters from this side, okay? Yes, that will be the point. So let us do this. We are saying a uniform beam. We have that. So, if we have two forces, P and Q, acting on this uniform beam, okay, at the respective distances as we are saying, okay, the distance of P from the turning point is going to be Cm, the distance of Q from the turning point is going to be Md or Dm, whatever. So, if these forces P and Q are acting on this uniform beam, then for this beam to be in equilibrium, then the moment about this point of this force about M must be equal to the moment of this force about what? About M. Are you seeing that? So we shall get the moment of P about M will be P times the perpendicular distance. And the perpendicular distance will be Cm. So P times Cm should be equal to Q times M what? MD. Okay? Let's write and say, if the two forces P and Q act on a beam, if the two forces P and Q act on a beam, if the two forces P and Q act on a beam, as shown, if the two forces P and Q act on a beam, as shown, if the two forces P and Q act on a beam as shown, the beam will be in equilibrium if P times Cm equal to Q times what? Md or Dm, whatever it is. This one is very simple because the forces are actually acting at a perpendicular distance. If you take the line of action of the forces, this is the line of action of this force, like that. And when you look at the turning point, is here. So just this is the perpendicular distance between the two. But what about if we have a case where a given force is acting, how do you pronounce this? How do you pronounce this? This is O. This is what? Obliquely. How about if we have a case when the force is acting obliquely? When we say obliquely, we are saying at a slanting what? Slanting position. Okay? Not at a perpendicular what? Position. How shall we handle that? You first write and say, suppose the arrangement is modified. Say, suppose the arrangement is modified. Suppose the arrangement is modified so as to appear as below. Suppose the arrangement is modified so as to appear as below. Suppose the arrangement is modified so as to appear as below. Suppose the arrangement is modified so as to appear as below. So as to appear as below, where the force Q, where the force Q, where the force Q, where the force Q, where the force Q acts act to act, where force Q acts like this, acts obliquely in bracket slanting position. Acts on obliquely in bracket slanting what? Position. Where the force Q acts obliquely in bracket slanting what? Position. Now this time round, we're going to have this. So this time we have so we have, this is A, this is what? B. We have our turning point is there. We have force what? We have this is what? Force P is acting here, okay? Then this time round, we have this that's our Q. This is point M. Now this time round, you see that Q is not acting. It is acting at a slanting position. This is it. It is acting that way. So now, for this body to be in equilibrium, what are we going to do? What are we going to do? Shall we say also its perpendicular distance of Q, the perpendicular distance of Q from the turning point is MB? Shall we say it is MB? Shall we say it is MB? What would be the turning point? I mean the perpendicular distance of Q from the turning point. What we do, we follow its line of action. Obviously, this will not be because it is acting at that point. I say that. So you cannot say this is perpendicular. When we say perpendicular, then the angle that is between the turning point, the line of action from the turning point, and then that given force or its line of action must be equal to, must actually be 90. But this is not 90. Okay? So what you do, you continue and draw. I think that you continue and draw the line of action of the force. So what I've done, I've drawn the line of action of the force. Then from here, I can have to measure at what point can I draw this to there, so that I can have an angle of what? 90 around somewhere here. Okay? So I keep adjusting. If it is not there, then I adjust here, so that I get, okay, until I get an angle of what? 90. I see that. Then I call this is point what? Point N. Therefore, the perpendicular distance of Q from the turning point becomes M what? MN, not M what? Not MB. I see that. Are we together? So when we have the force acting at an angle, a slanting position, you have to see a way of finding the what? The perpendicular distance. It will not be this one because this angle is not 90. I think that. So you look, you draw the line of action until you find the line of action of the force and the line of action from the given axis must actually give you what? An angle of 90. So if it doesn't give, then that doesn't become the perpendicular distance in that case. So in equilibrium, in this case, in equilibrium, we shall have that PA. I'll have this is as a C, okay? So P times Cm is equal to Q this times the perpendicular distance this time is mn, like that, not mb, not that. Very well. Let's try to be a little bit faster. Let's try to be fast. Right, and say where P times Cm is, where P times Cm is the moment of P about M, is the moment of P about M, is the moment of P about M, where P times Cm is the moment of P about M, is the moment of P about M, and Q times Mn, and Q times Mn is the moment, is the moment, is the moment, is the moment of Q about M, of Q about M. Full stop. New line writer, say not. Say not. Not. In this case, since Q is acting obliquely, since Q is acting obliquely in bracket slanting position, since Q is acting obliquely in bracket slanting position, since Q is acting obliquely in bracket slanting position, then MB cannot be its perpendicular distance from M. Then MB cannot be its perpendicular distance. Then MB cannot be its perpendicular distance from M in bracket turning point. From M in bracket turning point. Full stop. Yes, that.